So I'm very happy to be presenting today these results and on that I entitled the talk "Human Impacts on the Stratospheric Circulation." And yes, you pronounce this pretty well. It's Universidad Complutense de Madrid in Spain. That's where I'm working now. I just upgraded to assistant, or yeah, to some kind of professorship from postdoc. So okay, so I'd like to start by introducing the stratospheric circulation, and which you may not be familiar with, and in particular this Brewer Dobson circulation, which is what I'll be focusing on today. And it's transport circulation that transports mass, heat, and tracers globally in the stratosphere. And so you can see a schematic of this circulation in this figure. And these color contours show the ozone concentrations. So basically you're seeing here the ozone layer in the stratosphere, and the Brewer-Dobson circulation helps to shape or distribute the ozone within this ozone layer as it transports ozone to from its source region, which is in the tropical stratosphere, towards the high latitudes. And it also shapes the distribution of other tracers in the UTLS, or upper troposphere and lower stratosphere region, which is a region of particular interest for radiative forcing of climate. And it's also important because it contributes to shape the tropopause structure, which is important for convection and other aspects of climate. And one interesting aspect of the BDC, and probably not very intuitive perhaps, is that it's driven by wave drag from dissipating Rossby and gravity waves. And so here's a schematic showing where different types of waves break in the atmosphere. So you have synoptic, planetary scale Rossby waves, and then gravity waves breaking up at higher levels. And these this wave breaking and dissipation drives the Brewer-Dobson circulation. And as you can see, we only have this deep branch of the circulation in the winter hemisphere, and this is because we need a particular state of the background zonal winds in order for the waves to be able to propagate higher up and dissipate. And in particular, we need westerly winds for these Rossby waves to propagate. Okay, and another thing to point out here is that the gravity waves are not cannot be resolved in models because they have really small scales, so they have to be parameterized, and this is a source of uncertainty. So which are these human emissions that I'm referring to? I'm referring to anthropogenic emissions of two types. First, greenhouse gases. As an example, I'm showing here concentrations of CO2 taken from an IPCC scenario, the RCP 6.0. And so you can see that they increase monotonically throughout the last decades of the 20th century and also into the 21st century. And the other type of emissions are the ozone depleting substances. And these have a very different temporal evolution. As you can see, they increased very rapidly in the last decades of the 20th century. And after that, they are already starting to decrease, and they're projected to continue decreasing. And this is thanks to the Montreal Protocol, which is probably the most successful international environmental agreement to date. And it basically banned these emissions of ODSs, which include halogens such as CFCs that are well known. And thanks to that, we're already seeing this decline in these substances. And of course, the main effect of these ozone depleting substances is to deplete ozone, and in particular the ozone layer, and to create what we know as the ozone hole in the Antarctic. So here are the concentrations. Well, in October, the ozone concentrations in this region, in the Antarctic stratosphere, and you can see the rapid decline in ozone coinciding with the increase in ODSs. And then the recovery of the ozone layer, which we are already starting to see. These are model simulations, but the observations are already corroborating this recovery. So, what are the impacts of these external forcings on the bird ozone circulation? Let's start with increasing greenhouse gases. So it's well established now that increasing greenhouse gases accelerate the overturning bird ozone circulation. And so I'm showing here a figure for this latest generation of models, climate models, the CMIP6 models, and in particular here, these are runs with increasing CO2. And so what we get is an acceleration of the bird ozone circulation, so increased upwelling and increased downwelling, both in the deep and the shallow branches. And this is a very robust result across models, and we've seen this in previous generations of models, climate models, since over a decade ago. Okay. And also there's a very robust dynamical mechanism behind this acceleration of the BDC. And it's the following. So we know that greenhouse gases warm the troposphere and cool the stratosphere. And this leads to changes in the meridional gradients of temperature, which, as we know, are related to the vertical shear of the zonal wind. So we end up with these strengthened stratospheric zonal winds, which in turn, as I said before, are very important for determining where the waves can propagate and where they dissipate. So we have enhanced wave drag in the stratosphere, and this enhanced wave drag is what's driving the strengthened bird ozone circulation in the future. So this is quite a well understood mechanism. And what about the impacts of ODSs? Well, it's been more recently pointed out that increasing ODSs also accelerate the bird ozone circulation. And again, these are model results showing time series for time series of annual mean vertical velocity of this overturning circulation in 3 types of runs. So the first ones in blue are the all forcing runs. So they include both greenhouse gases and ODSs changing or evolving with time, as I showed before in the just some slides back. And then we have 2 sensitivity runs in which we isolate the effects of each of these forcings separately. And so we can attribute to each of them what's going on. And so if you look at the blue lines, you can see that there's an acceleration and increase of this bird ozone circulation, which is faster before the year 2000 than after the year 2000. So, and to quantify this is about a 50% stronger acceleration in the ozone depletion period before 2000 than after that. And if we look at the, and well, this is just for one model, I should say, but this result is consistent for multimodal means of several chemistry climate models. And if we look at the attribution here, looking at the individual forcing runs, we can see that it's clearly, this change in the slope is clearly attributed to the effect of the ODSs. Okay. And there's also a dynamical mechanism behind this contribution to the acceleration. And I should say that ODSs are also greenhouse gases, so one could think that they are contributing to this acceleration through the same mechanism as CO2 or other greenhouse gases, but actually it's been shown that this is not the main way in that they're acting, but the main way is through the ozone depletion. Okay, so ODSs are affecting the bird ozone circulation through ozone depletion. And the mechanism is this one depicted here. So we start from the ozone hole, basically. So these are trends averaged over the polar cap in the southern hemisphere in ozone. So you can see this ozone depletion, these negative trends extending through spring and summer in the southern hemisphere. And this ozone depletion leads to cooling of the polar stratosphere because ozone warms the stratosphere through as it absorbs UV radiation. And this cooling in turn, again, just to maintain thermal wind balance, leads to an acceleration of the zonal winds in this region and season, and that leads to enhanced wave drag in DJF in the southern hemisphere, which accelerates the broad ozone circulation in the southern hemisphere. And this, so here are the trends in the stream function of this circulation. So you can see that even if this is an ozone depletion and the ozone hole in particular is localized in time and space, the effect actually reaches the tropical upwelling, and it actually survives the annual mean. So this is the mechanism through which increasing ODSs accelerate the broad ozone circulation. Okay, so we've seen these effects of these two types of external forcings on the stratospheric circulation. But now the question is, do we actually see these trends in the observations, or is this just a model result? And to make this more interesting, the answer is no, we don't clearly observe these trends yet. And in particular, there's a discrepancy between models and observations regarding the trends in the BDC in the middle stratosphere in particular and upper stratosphere. And to illustrate that, I'm showing this figure showing trends in age of air, which is a magnitude that measures the residence time of air parcels in the stratosphere. So it's inversely related to the strength of the overturning circulation. And as you can see here, the values that we estimate from observations for these trends are positive, so indicating a weakening actually of this circulation. While the models, these are results for two different generations of chemistry climate models, they actually show very robust negative trends, as I showed before. And the only region where we actually see an agreement is in the lower stratosphere, but there's a clear discrepancy at higher levels. And as you would think, there's a lot of work that's been done right now in the community to understand this discrepancy. And one important thing that we need to consider is that we cannot measure directly the broad ozone circulation strength. And so we have to estimate it indirectly from measurements of real tracers that are long-lived tracers. And there's a lot of assumptions that have to be made in deriving the strength of the circulation out of those tracer concentrations. So this is a source of uncertainty. And another one is the limited sampling of the observations. So we either have global satellite observations over short periods for these tracers, or we have longer time series, but in situ observations of more limited spatial coverage. And yeah, so that these two sources of uncertainty lead to these large error bars that you're seeing here in the observations in black. And but overall the trend does not agree with the models, which are shown here in the colors. And on the modeling side, the main uncertainty probably is coming from the fact that the gravity waves are parameterized, and we're not sure about what they will be doing in the future. So one thing we did in this paper is to subsample the model time series as the observations. So we took the time series phase of air from the models and subsample them only in the places and times where we have observations, and calculate the trends only out of those points. And the result is shown here on the right. So here are the trends Now for the observations in gray with these large error bars, these are two different observational estimates of the age-over trends, and then all the model results for different models and model members. And you can see still that models give negative trends and observations give positive trends. But there's also another result is that we have now on part of some of these model simulations are actually compatible with observations in the sense that error bars overlap. Okay, so of course this is not an agreement, and there's still a lot to do to understand this, but this goes in the direction of warning that we need to make a more apples to apples comparison in order to better understand this discrepancy and to try to reconcile results. Okay, so just to summarize, here are my 3 take-home messages. First, anthropogenic greenhouse gases and ODS emissions accelerate the stratospheric reduction circulation, which has implications for surface climate and also for the ozone layer. And then thanks to the Montreal Protocol, we know that ODSs are declining now since 2000, and this is reversing the effects of ozone depletion on the BDC. And then this final warning on the still remaining open question, the discrepancy in the trends between models and observations regarding BDC trends in the middle stratosphere, which is an open question right now in the community. So thank you very much, and I would welcome any question that you have. Thanks.